Go ahead.
Okay, good morning. So I'm Takanori Sasaki from Kyoto University. So my lecture is about the length of a day. 4 questions before I answer the final question. Okay, so how long was a month? How to make the moon? Why moon is moving away from the Earth? How old are the Earth and the moon? Then, at last, we can answer the question, how long was a day on the Earth? So, first question is, how long was a month? Anyway, do you have any idea to measure the distance between Earth and the Moon? Of course, it's impossible to measure the distance using a measure, you know. So, how to measure? Yes, we use time. So, by using the beam, laser beam from the Earth and reflect on the surface of the Moon and coming back to the Earth, then we can measure the round trip time. And since we know the velocity of the light, 3 times 10 to the 8 meters per second, so we can derive the distance between the Earth and the Moon using the measuring the round trip time. Yes, it's a very clever way to measure the long distance, right? And actually, NASA used this method to measure the distance between the Earth and the Moon. So the project name is the Lunar Laser Ranging Experiment. So the first reflector was positioned on the Moon in 1969 by Apollo 11, maybe Apollo 11 astronauts. So the first, so then using the laser, so like this one, using the laser, they measure the distance. It's about 384,400 kilometers. It's very accurate. Yeah. But they also found more surprising fact later. They analyzed the data from the LLR experiments from January 1992 until April 2001 to measure the Earth-Moon distance at each time. Then they compared the results each other. Then they found the Moon is moving away from the Earth at a rate of 3.8 centimeters per year. So if it's correct, it said the Moon was much closer to the Earth before. It's a very surprising fact, isn't it? I don't know if it's correct or not. But so I have the next question. So when the orbital distance of the Moon is changed, then what happened? Do you remember the Kepler's third law? I think you have studied when you are high school students, maybe. So the Kepler's third law said the square of the rotational orbital period of a planet is directly proportional to the cube of the same major axis of its orbit. So, and this law is also applicable to the Earth-Moon system instead of the Sun-Earth system. For the Earth-Moon system, it means the closer the Moon locates, the faster the Moon revolves around the Earth. While the further the Moon locates, the slower the Moon revolves around the Earth. So, since the Moon was much closer to the Earth, according to the NASA's experiments, then the Moon must have revolved around the Earth much faster than today. Did it really happen? Yes, it did. I will show you it really did happen. So this is the maybe historical paper. So by Kahn and Pompey. So they proposed the way to estimate how long was a month on the Earth. So they said daily growth lines and lunar monthly sept are formed in Nautilus Pompilius linearis shells. Sorry, I don't know how to exactly. So, but some types of shells. So using some types of shells, and the number of days per lunar month can be determined using the fossil shells. And the number of growth lines per chamber length between these arrows, so 1, 2, 3, 4, 5, 6, 7, can be counted using a scanning electron microscope. So they used the technique to count the number of lines in the chamber, and they estimated that how long was a month. So this is their results. The horizontal axis is the age of the fossil shells, and the vertical axis is the growth lines per chamber, which means how long was a month. And the right-hand vertical axis is the Earth-Moon distance normalized by the present distance. So, as you know, the present the shells have 30 lines in the chamber, so it means there are 30 days in a month, of course, you know. But if you see about 400 million years ago, there were only 9 lines in the chambers. So it means about 400 million years ago, there were only 9 days in a month. And consequently, the distance between the Earth and the Moon was about 40% of the present value. And so their paper is somehow controversial. So the accurate number, so 9 days or 9 days is so. I don't know it's correct or not, but Moon was much closer than today. Is right, I think so. So the first conclusion of my talk is that the Moon was much closer to the Earth and revolved faster. Okay, so we have known that the Moon was much closer to the Earth. But why? So let's move on to the next question. How to make the Moon? And how to locate the Moon so close to the Earth at the beginning? Until 1970s, many hypotheses about the origin of the Moon have been proposed. So here I show you 3 famous hypotheses. So the first one is the fission hypothesis. So it said ancient spinning Earth expelled a piece of its mass, and the piece became the Moon. This hypothesis was rejected because this cannot account for the angular momentum of the Earth-Moon system, which means the Earth-Moon system should have got a much larger angular momentum according to this hypothesis. So it has been rejected. The second hypothesis is co-accretion hypothesis. The Earth and the Moon formed together using the same nearby building blocks. This hypothesis also has been rejected because this cannot explain why Moon has a relatively small iron core compared to the Earth. Which means the Moon should have same compositions as that of the Earth based on this hypothesis, so it has been rejected. Okay, so last hypothesis is Kepler hypothesis. So in this hypothesis, Moon was formed in other place, then moved to near the Earth, then was captured by the Earth. Unfortunately, it also was rejected because close encounter with the Earth typically results in either collision or altered trajectories, which means the possibility of capturing the Moon by the Earth should be too small to occur. So, all hypotheses has been rejected around the 1970s. Yes, it's very awful situation. Then, how to make the Moon? I introduce you to the most fantastic, most exciting, but of course most promising hypothesis. So, which call it the giant impact hypothesis. So this hypothesis was originally proposed by the two research groups almost simultaneously. So the Hartman-Davis 1975 and the Cameron Ward 1976. So this hypothesis assumes the Mars-sized body collided with the proto-Earth, the last stage of the formation of the solar system. Then this collision produced a lot of fragments around the Earth. And then these fragments accreted together to big body. Then it became the Moon. Yes, I know, it seems crazy. Yeah, it seems crazy. So, but fortunately, thanks to the recent progress of numerical simulations, now we have shown that the formation of the Moon by the giant impact can actually happen. So I will show you the numerical simulations. So first one is the giant impact simulations by using the SPH method. SPH means the smooth particle hydrodynamics. So this is simulation. So the Mars-sized body collided with the proto-Earth, and then the large amount of fragments can be produced around the Earth. So they said, or they concluded the giant impact between Earth and the Mars-sized body can produce a moon-forming disk. You see, disk-like systems. So giant impacts can produce the building blocks of the Moon, but it's actually accrete to one body. Yes, I show you. So next simulation is the in-body simulations for the formation of the Moon, simulated by myself recently. It's very easy to simulate nowadays. Okay, so the proto-Earth and these red circles represent the giant impact fragments. The size of which circles represents the real size of the fragments. So, okay, see how to accrete. So okay, so you see. Yes, I did it. Yes, we can accrete the fragments to one body, to one big body. So then I show you where the Moon was formed. So this another red circle is the Roche limit. Roche limit means the inside the Roche limit. So around here, inside the Roche limit, the tidal force by the Earth is stronger than the gravitational force. So the fragments cannot accrete each other. On the other hand, the outside of the Roche limit, the gravitational force is stronger than the tidal force. So the fragments can accrete together and to be a big body. So because of that, the moon was formed at just outside the Roche limit. But Roche limit is just 3 times Earth's radius. So since the moon locates at 60 times Earth's radius, originally the moon was formed very, very closer to the Earth than present. So it's the results of the numerical simulations. Yes, okay, so we have some break here and see a beautiful computer graphics movies. This movie is based on the numerical simulations. So the Mars-sized body collide with the Proteus. Then, giant impact is very, very massive event. So at the beginning, just after the giant impact, so almost all rocks are vaporized and surrounded by the Proteus. And then cooling down, then to become liquid phase, then cooling down to become a solid phase, to be material. So we are building blocks of the moon. It's a good question. So based on the numerical simulations, the impact as body, so the moon's composition is almost all from the impactors. Yes. So okay, become to a liquid phase, and some fraction became the solid materials. So it's, of course, it's a computer graphics, but it's based on the numerical simulation. So this movie is somehow real, So don't worry. So it's real situations. So in this disk, each small bodies accrete to one body. So this one is becoming larger and larger. So because the larger body has much strong gravitational force, so one body becomes larger and larger. We call it runaway growth. So this body is a runaway growth body. So these interactions is also based on the numerical simulations. It's surprising, right? So after some time means very short, like 1 month to 1 year. So yeah, very short time. So the moon has been formed. So the moon was formed just outside the Roche limit. Okay, thanks to the simulations and the visualization. Yes, so based on this hypothesis, so many facts are consistent with this results, with this outcome. So like moon has a very small iron core because after the giant impact, fragments is a rocky component, has rocky components. So just using a rocky component to make the moon, so it's consistent with the real data like that. So there are many there are many, so yes, good point and better point than the other hypothesis. So the second conclusion of my talk is Moon was formed nearby Earth by the giant impact. And the Moon was located very closer to the Earth. So next question is, why Moon is moving away from the Earth? Answer to this question is very simple. Just exchange of angular momentum. So you can see the explanation of that in the textbook, Solar System Dynamics, which is kind of a Bible for planetary scientists. So very, very thick textbooks. In this textbook, so it is highly likely that the orbit of the Moon and the spin of the Earth have changed considerably over the age of the solar system, due in particular to the action of the semi-dural tide raised by the Moon on the Earth. So, I got it? Okay, I know it's not easy to understand just reading this sentence. So, I will explain the mechanism of exchanging of the angular momentum using a simple cartoon. So, don't worry. This is the Earth with the ocean and the Moon. So, Earth rotates itself and the Moon revolves around the Earth. They are pulling each other by the gravitational force. Then the tidal bulge are raised in the ocean because the ocean, is movable, and the Earth itself is rotating. So the Earth's rotation displaces the tidal bulge a little bit. Then the Moon attracts the tidal bulge. It means the Moon pulls the Earth backwards. Okay, so the Earth slows down because by losing the angular momentum. So, okay, you see. So this arrow you see. So slow down. Okay, slow down by losing the angular momentum. On the other hand, for the Moon, the tidal bulge of the Earth attracts the Moon. It means the bulge pulls Moon forward. So Moon speeds up by gaining the angular momentum from the Earth, then moves outward because the Kepler's third law. So gaining the angular momentum, Moon speeds up and moves outward. Yeah, it's very simple. It's a very simple mechanism. It's not so difficult to understand using the cartoon. Okay, so I think you have understand that. So that is why the Moon is moving away. So the third conclusion is the Moon is moving away by gaining angular momentum from the Earth. Fourth question is, how old are the Earth and the Moon? So, sorry? Steady state is very far future. So not now. So it's moving away now. No. No, not so. I mean, how to say? So limit is existed. Yes. So how old? But how old is how old? So since the Moon was formed by the giant impact, so the age of the Earth and the Moon corresponds to the time when the last giant impact occurred. Okay. But how to get the time? So I introduce you the very clever way to measure the time. So it's called radioactive dating. So this is an example of the radioactive dating using the uranium and lead. So uranium, 238 uranium is a radioactive nucleus. So it decays to the thorium, so it decays to thorium and decays to another, and decays to another. Then finally decays to the 206 lead. And the decay time or half-life time of decaying is about 4.5 billion years. Okay, so how to use the system? Let's consider the objects which contains only uranium at the beginning. After the half-life time, half of the uranium decays to the lead. Then another half-life time, the half of uranium decays to the lead. Then 2 over 1 decays to the thorium, to the lead in another half-life time. So, by measuring how much amount of the lead is contained in the objects, then we can estimate the age of the objects. Okay, so half of the example, so the half of the lead, then we can say that this object, the age of this object is tau, but just one of 8th uranium is contained, then it's the age of the object is 3 times tau, like that. For estimation of the age of the Earth and the Moon, we use hafnium and tungsten instead of the uranium and lead. So, because it's a very good chronometer, so its chronometer, the 182 hafnium decays to the 182 tungsten with a half-life time of about 9 million years. So, it's a very good chronometer because the hafnium is lithophile element, which means hafnium likes rocks. So it's incorporated to the mantle. On the other hand, the tungsten is siderophile element, which means tungsten likes iron. So it is incorporated into the core. So this system is the ideal chronometer for metal silicate segregation. So as you see the graphical some movies, so a giant impact is very massive event. So it can produce a global magma ocean on the proto-Earth, which seems to lead to a considerable metal silicate segregation at the time. So hafnium tungsten age would be the age of the last giant impact, that is the age of the Earth and the Moon. So we can use this system to estimate the age of the Earth and the Moon. So in this system, so we have to measure how much amount of 182 tungsten is contained in this mantle's part. So this tungsten. So then we can estimate the age. Okay. This is the latest measurements of the hafnium tungsten ratio in many types of rocks from the Earth and also from the Moon. So anyway, according to this data, so they concluded that the Earth and the Moon was born at about 62 million years after formation of the solar system. As you know, the age of the solar system is about 4.56 billion years. So it's very longer than the 62 million years. So it said, it means the Earth and the Moon were born at the very beginning of the history of the solar system. So, The fourth conclusion is that the Earth and the Moon were born at about 4.5 billion years ago, the very beginning of the solar system formation history. Okay, at last, we reached the final answer. So we can answer the final question. How long was a day on the Earth? This is the answer to the question. The horizontal axis is the Earth-Moon distance, normalized by the Earth's radius, and the vertical axis is the length of a day. And this line is estimated based on the exchange of angular momentum between the Earth and the Moon. So, at the beginning, Earth-Moon distance is about 3 Earth's radius, just outside the Roche limit. So it's very closer to the Earth. And we can estimate the length of the day using the angular momentum. Angular momentum exchanged from between the Earth and the Moon. Then, surprisingly, so the length of a day at the beginning is just 4 hours. Then after 30,000 years, the length of a day became longer to the 6 hours. Then after 60 million years, became longer to the 10 hours. Then now, the Earth-Moon distance is about 60 Earth's radius, and of course, the length of the day is 24 hours. Then in the future, it's very far future, but in the future, maybe the length of a day would be 47 days. But don't worry. So it's very far future. So don't worry to work so long time a day. Okay. Yes. So finally, I show you the correspondence relationships between the length of a day and the history of life on the Earth. So, sorry, I'm not expert to this field, so I don't know it's so correct or not. But anyway, so there is evidence of life around here, and emergence of the photosynthesis around here, emergence of eukaryotes around here, and the emergence of much cellular life. Then humans was born at very near here. So yes, I think it's somehow suggestive figures for everyone, isn't it? I think so. Okay, so it's my last slide, and so last message of my lecture. Our ancestors must have lived on Earth, a day of which was shorter than today. So, conclusions. Moon was much closer to the Earth and revolved faster. Moon was formed nearby Earth by the giant impact. Moon is moving away by gaining angular momentum. Earth and the Moon were born at about 4.5 billion years ago. And the last message is a day on the Earth was much shorter than today. Thank you very much.